Hey everyone, Geek37 back with another video. And in this video, which is part 3 in my Exploring the Heptagonal Triangle series, what I'm going to do is I'm going to prove an identity using the squares of the sides. So b squared over a squared plus c squared over b squared plus a squared over c squared will equal some value. This identity is necessary for other proofs that I'm going to do down the line in this series. So what I'm going to start off with is going over again what the side lengths mean again real quick here. So we'll draw a quick triangle here. We'll call this A. We'll call this B, and we'll call this C. A is opposite of angle A. Angle B is opposite side B. And C is opposite angle C. The angle measurement at angle A is pi over 7. B is 2 pi over 7, and C is 4 pi over 7, just like that. And we had some identities that we proved in yesterday's video that b squared equaled a squared plus ac, but I had shown the factored form of a plus ac. I'm going to be using the unfactored form throughout this video. The other ones were in c squared equals b squared plus ab. Of course, we factored that out as b times b plus a. And then a squared, this I did not show, but this is a rearranged form of c squared, or a squared plus bc equaling c squared. Well, a squared equals c squared minus bc. You can factor out the c to get c times c minus b. And then, of course, the fourth one is ab plus ac equaling bc. I'm not going to show the factored form there because it won't be necessary in this video. So what I'm going to do is, as you can see on the left side of the screen, we have our fractions, the sides being squared. I'm going to replace the numerators with their associated forms. So b squared, I'm going to rewrite that as a squared plus ac over a squared. And you'll see why I'm doing that here shortly. C squared equals b squared plus ab all over b squared plus replace a squared with c squared minus bc all over c squared. And you could probably see it right away. I'm not going to show the full algebra of this because of time and space constraints. But as you can see here, we have a squared over a squared, b squared over b squared, and c squared over c squared. Again, we have two terms in the numerator. You can factor those as two separate fractions if you want. And then we have the second part here, ac over a squared, ab over b squared, and bc over c squared. Now what happens is, as you can see, we have a squared over a squared. I'm going to go down here and write that as 1. After that, a plus sign, and you can see ac over a squared. I can cancel the a's, so I'm left with c over a. Plus, on the next part, b squared over b squared will equal 1. And then after that, another plus sign. We have ab over b squared. We can cancel the b, one of the b's. We get the fraction a over b. And then on the last one, we have c squared over c squared. We get a plus 1 there. And then minus, we got bc over c squared. I can cancel one of the c's, minus b over c. Now, the nice thing is we have 3 1s. Those add up straight together to be 3 plus, and then I have the rest of my fractions, c over a plus a over b minus b over c. Now, the interesting thing is, how do we proceed? Well, what I'm going to do is I'm going to find a common denominator for the first two fractions, and you can see why I'm doing that. A times b, well, is just ab. Now we cross multiply. The simplest way to do it, we get bc plus a squared and minus our last fraction of b over c. Now notice here we have bc plus a squared. Well, bc plus a squared, well, that's just a rearrangement of the third identity. That was what I showed yesterday in the video on those Ptolemean identities. And I call them that because we used Ptolemy's theorem to find them. What I'm going to do is I'm going to replace that numerator with c squared over ab minusing bc. Now what I'm going to do next is interesting from there. I have a c squared here. What I'm going to do is I'm going to replace c squared with its associated b squared plus ab terms. So we'll get b squared plus ab over ab minus bc. Now you'll see why I'm doing that. Take a look here now. We have ab over ab, and of course, we have b squared over ab. So, like before, I can cancel off one of the b's. So I get b over a, and of course, I got a b over ab. So what I'll do, go up here. Hopefully I have enough space to show this. I'll get 3 plus b over a plus 1 minus bc. So 3 plus 1, that'll equal 4. So I'm left with b over a minus b over c. So what we'll do the same thing as before. We'll find a common denominator here. We'll get 4 plus ac. We'll cross multiply. We'll get bc minus ab. Now, where does that leave us? Well, that leaves us with now our fourth identity right here, AB plus AC equals BC. What I can do is I can rearrange that as BC minus AB, and that will equal AC, just like so there. So what I'll do is I will replace BC minus AB with AC over AC. So I get 4 plus 1, that will equal 5. So what happens is I get B squared over A squared plus C squared over B squared plus A squared over C squared equaling 5. And that concludes the derivation right there. Now, again, the reason why I showed this particular identity is because I'm going to be using it in later videos to prove some trigonometric relations. And I also did it because it is it's basically a logical corollary that came from those Ptolemean identities, and it also showed up in the articles on the heptagonal triangle on both MathWorld and Wikipedia, and I wanted to show that to you today. All right, I hope you enjoyed this video. I enjoyed making it. This is Geek37 signing off.